So good morning, everyone. My name is Declan, as Randy's alluded to. I'm a final year engineering student here at University of Canterbury, and this morning's presentation will be on the comparison of 3 flood flow estimation methods within New Zealand. These are important as they can have consequences in economic and environmental aspects, especially around being designed too small and blowing out in heavy rainfall instances. The objectives of this project was to compare and analyse the empirical rational Team 61 and a regional method, which was designed by Mr. Henderson, who's with us today in the Zoom, and his fellow colleague, Mr. Collins. And these were compared across 100 New Zealand catchments. The secondary objective was to analyse the 3 methods across Canterbury, Bay of Plenty and Northland to identify any regional trends that may be present. The methodology for the use of the regional method, or our regional method, NEWA's version was used, which is an online interactive tool. So where the desired catchment was clicked on, you zoom into a stream segment and click it, and it gives you a flow estimation, standard error, and the area that the flow was calculated for. For the rational and Team 61 methods, catchment characteristics were determined using Google Earth Pro imagery and its design tools, and New Zealand topography overlays were downloaded and then uploaded into Google Earth to be used to identify stream lengths and stream slopes. So the analysis was conducted on 100 smaller catchments, which are all less than 10 kilometres squared in area. Ben Costley, who did a project last year on the comparison of the rational and Team 61 methods, also conducted an industry survey which found catchments less than 4 kilometres squared were more desirable. So as the distribution shows, catchments less than 4 kilometres squared were more heavily represented, but there was a small representation of larger catchments up to 10 kilometres squared as well. One of the main things being identified last year in his project was that the main cause of an outlier was the classification of topography factors for both the Team 61 and rational methods. So I decided to try and standardise the way these were selected as best I could. I decided to use a drainage map available online, produced by Land Information New Zealand, to classify the soils needed for the Team 61 WIC factors. So using, as the key shows, there was 5 soil drainage classifications, and I paired these with its corresponding Team 61 soil classifications, which is shown on the left there of that slide. So the connections made in this table relate to the soils on the left-hand side there, and then using Google Earth imagery, the appropriate topography factor was chosen. Pumice soils were excluded due to the fact that there was a study saying that it's very variable in how caution should be used when using 0.4 and 0.5 values for pumice soils. So the same was done for the rational C factor, and as the table shows, I used stream slope and the topography cover to select the required value. The value ranges were gained from the table shown in the low volume roading engineering best managed practice guide. So that's where the range of values came from. Stream slope was used as that was a characteristic I'd already calculated from Google Earth Pro, and it was just handy for me. And then once I'd gathered all the 100 catchment characteristics, I had a pretty good idea of how these slopes should be separated into their 3 categories there. So it was a simple method where you just identify the slope of the stream, go to that column, and then line it up with its corresponding topography row. So the results this is just a sample of 15 catchments. All these catchments, these 15 are ones that are less than 100 hectare. And there were some recognisable trends found. Can be seen in catchments 80 and 80, 92 and 22. They all follow similar patterns where the NIWA method gives the highest estimate, followed by the rational and the TM61. Generally, the rational and the NIWA method followed pretty closely throughout. But as can be seen in catchment 75, there were occasions, or catchment 75 in particular, gave a very low NIWA flow. But catchment 75 and 74, the rational method had the ability to, on occasions, give much higher estimates than both methods, which sort of stood out from the regular trend with the NIWA method. So regression analysis was conducted where each method was compared against each other. So the black line in the figure shows where both methods would give equal flows. This is just an example of one of the three relationships found. This one shows the relationship between the NIWA and the rational method. The catchments are classified by area using the colour system on the right of the figure there. And it can be seen as area increases, the variability in flows between the rational and NIWA method also increases, with estimates becoming larger and further apart. So this is just this summary of the relationships that we found and their corresponding R-squared values. So it can be seen that the rational and TM61 methods held a reasonably strong relationship, while the TM61 and rational methods held a relatively low relationship with the NIWA model. So the overall trends for 95 New Zealand catchments, 5 catchments were excluded, as under my WIC classification for the TM61 method. 2 flows were unable to be produced, and 3 flows using the NIWA method were unable to be located, as I was using previous data collected by Ben Costley last year, and some of his coordinates I think may have just been slightly recorded wrong, and a stream path couldn't be located on the flood frequency tool. So the overall trend showed that the TM61 method produced the lowest flow 66% of the time, with the NIWA model producing the lowest flow the remaining 34%. The rational method produced the highest flow estimate 63% of the time, with NIWA presenting the remaining 37%. I conducted further analysis where I applied the flows calculated to the application of culvert sizing. I analysed the regional differences, and as the NIWA method gives flows for a segment of stream rather than a flow point, it gives the largest flow for the largest catchment along that stream instead of the same area as what I had. So I attempted to make an adjustment to see if that had an impact on the flows calculated. So this is results for the same 15 catchments as previously presented. I also incorporated the Talbot's method to see how that would align with the 3 methods already analysed. I used a hydrograph provided in the New Zealand Forestry Engineering Manual to produce the flows generated for the TM61 rational and NIWA methods. As the graphic shows, the TM61 method regularly, as would be expected from its flow estimates, produces the lowest or the smallest culvert diameter, while the NIWA and rational method, and also the Talbot method, surprisingly, follow relatively the same trend across all of the 15 catchments. Breaking it into the regional analysis, these are a couple of standout points. Was that in the Bay of Plenty region, the lowest flow estimate, different to the Northland and Canterbury region, was predominantly produced by the NIWA method at 75% of the time, and the highest flow estimate was heavily favoured by the rational method, also in the Bay of Plenty, which didn't have as even as a spread between the 2 methods as the Canterbury and Northland regions. Also, the Northland region heavily favoured the TM61 method to produce the lowest estimate. It was believed from a study back in 1971 that was conducted on 6 gauge catchments that the TM61 and rational method both overestimated on pumice soils, and there's a large amount of pumice soil in the Bay of Plenty region, which leads me to believe that these results may have impacted on the 2 methods, producing higher TM61 and rational methods than the other 2 regions. So as I talked about, to adjust for the flows produced by the NIWA method not equaling my exact catchment study area, an adjustment was made using the area ratios to the power of 0.8. This adjustment was made through the interpretation of a 2009 study with the notion that flow decreases, but it doesn't exactly decrease in a linear manner. So the figure shows the red is the adjusted flows of the NIWA, while the grey is the original. And as can be seen in figures 92 and 22, it has a substantial impact on the flows and reduces them by a reasonable amount compared to originally. You'll see that a couple of adjusted flows slightly increase. This was due to the Google Earth Pro tool. I accepted an error of difference in between my area and the NIWA's area of less than 10% of my my catchment's area size, if that makes sense. It's just that I think the NIWA tool might have used ArcGIS and I used Google Earth Pro, so there was going to be a slight difference in areas calculated, but from the results, the increase is very minimal. It didn't have too much of an impact. So the conclusions I made is I confirmed that the TM61 method regularly gives the lowest estimate throughout New Zealand. The rational and NIWA methods share the highest estimate more regularly. There was a strong relationship found between the TM61 and rational methods, but a relatively weak relationship between the TM61, rational, and the NIWA method. It was found across the entire 100 catchments, or 95 catchments, that the rational method consistently gave high estimates in the TM61. The adjustment of the NIWA flows to resemble the desired catchment area is likely to reduce NIWA flows to align more closely with the flows generated by either the TM61 or rational methods. The Talbot method, although prone to greater culvert diameter estimates, shows a closer relationship than expected to the rational and NIWA method culvert estimates, and that the regional differences, there was a regional difference with the Bay of Plenty showing different standout characteristics than both the Canterbury and Northland regions. Thank you.